Hello there, my name is Ramon, and today I'm going to be walking you through an example on how to use Qdrant for image data. In particular, we're going to be walking through an example on how to use semantic search with Qdrant to accurately search for images that contain different kinds of skin diseases, in particular melanoma, which is a type of skin cancer that one can get. So we're going to be using Qdrant today. We're going to be using the Transformers library, and when we're also going to be using the datasets library. So why do we choose this example? Well, we chose this example because if you think about doctors going through a lot of patients in a day or a lot of samples of a particular disease or illness, you can imagine that your eyes get tired or you are not as efficient at detecting and evaluating a medical sample in, say, after 17 hours of work, of being at work, than you are when you get there the first thing in the morning. So, what if you had a system that allow you to take a sample, like an image of a skin condition, put it into an application, and then the engine behind the application will allow you to search for similar images. Now you have the actual sample that you're trying to evaluate, and you have a point of reference. Images with the exact same disease, with some particular quirks, like for example, low light, or the skin had a tattoo where the particular area with the skin condition had a tattoo around it or something similar. So that's the motivation behind this. So how can we help a person evaluating images with skin conditions assess difficult ones in a much better way, or have a point of reference to compare one with another? So the data set that we're going to be using is available in Hugging Face, and it's called the manual, or this person uploaded it, and it's called the skin cancer dataset. So the HAM1 10,000 dataset, a large collection of multi-source dermatoscopic image of common pigment skin lesions. And I have a link in the notebook, which you will also be able to access via the summary in the YouTube video for this video. So with a short description of the elements that we have in this dataset, or the features that we have in this dataset, we have the image, which is a 600 by 450 image. We have the unique IDs for the images, the lesion ID of the skin condition of the patient. Then the DX is for the diagnosis given to the patient. DX type is the type of diagnosis that was given to the patient. So in one we have melanocytic nevi, which I don't know a lot about skin conditions, but it's a type of skin condition. Melanoma, which is cancer in the skin. And then in the type, we have histo. What kind of diagnosis was it? Did this person come for a follow-up? Was it a consensus? Did more people look at this image, not just one doctor, and so forth? The age of the patient, the gender of the patient, and then the localization of the skin condition, for example, lower extremity, upper extremity, and so forth. All right, so a couple of things that you are going to need. Make sure you create your environment and that you have Python at least 3.10. You can use 3.9 most likely and 3.8, but use 3.10 to follow along exactly as in this tutorial. You're going to need the Qdrant client. You're going to need transformers, dataset, torch, and NumPy. Then the next thing you're going to need the Qdrant image, and you're also going to need Docker install to be able to pull the latest Qdrant image. And then once you do, you're going to be able to run Docker with the following command here. So let's actually get our Qdrant instance started, or container started. So as you can see, I am running right now v1.2.x, but I believe as of this week, there's a version v1.3 already available. So you're also more than welcome to use the latest one. As a matter of fact, I encourage you to use the latest one. Okay, so we're going to start by importing our modules. Now that we have an instance of Qdrant running, we are going to connect to it. We're going to use, since we are using the port 6333, we are going to connect to that port with the Qdrant client. We're going to create a collection. And if you've seen some of the previous videos on how to get started with Qdrant, then you know that a table in a normal database is similar to in a collection in Qdrant. So a collection in Qdrant is going to be this set of points. Points are vectors, the representation that we get from unstructured data or even structured data, to be honest. Then we're also going to have an ID, and we're going to have a payload. A payload is going to be additional metadata or information about the vector. So we're going to have, that's what we call a point. And Qdrant, and in Qdrant, many points are called a collection. So we're going to create our first collection. It's going to call image collection. We're going to give it the parameters that we're going to be getting from our model. It's going to be 384 dimensional vectors. Then we're going to give it the cosine distance metric to find similar matches from one skin to another. You can see we created our collection, image collection here. I'm going to close this out. And then we're going to start working on our image embeddings. So, and if you have never heard of embeddings or um, never dealt with them, an embedding is a representation of some piece of data. And this representation was created by passing many samples of data through a deep neural network, more often than not, and extracting the representation of this piece of data from inside the network. So in particular, the one of the most common ways of extracting these embeddings nowadays is with transformers. And today we're going to be using a vision transformer. But before we get there, let's actually load our dataset. I had already downloaded it, and if you haven't yet, it's going to take a little bit. It's not a super large dataset, but it might take you a couple of minutes just to download it, depending on your internet speed. I do have it cached in my machine, so that's why it loaded so quickly. And as you can see, we have the exact same features that we talked about a little bit ago. So let's evaluate one of them. Here we have the image object with our 600 by 450 image. We have the image ID, the lesion ID, the type of diagnosis, or the diagnosis, the type of diagnosis, the age of the patient, the gender, and then the place in the body of the person where this was found. Okay, next we can evaluate one of the images. So in this particular one that we selected above, 8,000, the image at index 8,500, we have a case of melanoma, which is skin cancer. And if we select the image from the sample, then we can see that what the melanoma looks like, and it looks quite painful, if you ask me. Okay, so what are we going to do? How are we going to extract these embeddings? How are we going to extract these vector representations from unstructured data? Well, the way in which we are going to do it is that we're going to use a model, a pre-trained model. A pre-trained model is like think about it as a teacher, or as a person that could teach you something, a person that has some knowledge about a particular domain and doesn't need to start from zero. If we were to start learning how to ride a bike, we will, and we don't see anybody doing it before us, we'll probably won't get it right the first, second, third, and fourth time. If we've only if we've only used a mountain bike before, but then we see a marathon bike next to it, if we've used one, then we're probably going to be able to use the other one because the mechanics are quite simple. So that's kind of the difference, or that's kind of the analogy that I want to make here. That if you have seen an example before, and even if you are working on a different one, if it is similar to the one that you learned before, then it's going to be much easier for you to do another one. So that's the pointing case for these pre-trained models. We're going to use a model that already knows something about analyzing images, and then we're going to use it to extract these vector representations of the data that we have. And in particular, we're going to use the Dino model, which was released by Facebook a few years ago. And as a matter of fact, so this was in 2021. And not right now, a couple of months ago, Facebook released version 2 of the Dino model, and it's 10 times better, if I'm not mistaken. So as you can see, it allows you to extract these representations from images, and it's actually quite cool. So I highly recommend that you check it out and learn a little bit more about it. Okay, so we're going to load PyTorch, and then I have a CUDA device in my machine. If you don't, then you're going to go straight to the CPU, and it's going to take a little bit longer to run the following cells, but still, you're going to get to it no matter what. So we have here a two classes from the transformers library, VIT image processor and VIT model. The VIT image processor is going to allow us to extract features that we're then going to use to pass in through our trained model. So you use the trained model to extract features from different images, and then you use those features to then make a prediction or extract the embeddings from the actual model. So we are also so the difference here is that when you create the image processor, you don't pass this object to your GPU, but you leave it there. You pass each element, and then you do pass the model. You do put the model inside the GPU. Okay, so let's look at an example of what we're talking about here. So here we have a vector of four, or a tensor of 4 dimensions. In the first one, we have the batch, or how many do we have? We only have one element. Then in the second one, we have the channels, or RGB, red, green, and blue channels. And then in the next one, we have the pre-processed image. So remember, we had a 600 by 250 image, and now we have a 200 by 224 by 224 image. And then in the next one, what we have is the pixels. So the tensor. And so this is what we're going to pass in through our model. And then if we want to extract one embedding, what we can do is we can use this Python semantic or Python way of unpacking a dictionary. We put star star, and then we're going to select the last hidden state from that image. So let's look at what we have. What we get back is, again, batch size 1, because we only have one image. And then we get 197 tokens, and then 384 embedding vectors. So remember earlier when we created our collection, we had 384 vectors. So what is this 194 and 197? So when a model has been trained, it has been trained with a particular set of, with a particular architecture. And transformers, in particular vision transformers, what they do is that they take an image and they split it into squares, and then they put all of these squares into one big vector. So you have patches of an image that you're going to analyze. You don't analyze the entire image at once. So what it has here, what the tokenization process has done, is that it has split this image into 197 patches, and then we have, for each one of them, 384. So what we actually want to do is we want to condense all of that into one vector. And one of the ways in which we can do this is by mean pooling. So if we take that vector that we just got and we select the mean or the average of the first dimension, so dimension 0, dimension 1, dimension 2, then you will see that we have one vector of 384 dimensions. And this is exactly what we need. These are the vector representations that we're looking for. So how do we do this for the whole data set? Well, for the whole data set, we will create a function. We're going to say get embeddings, and then we're going to use the inputs. We're going to call our preprocessor. So here we're taking a batch because we're going to send this to our data. We're going to use this with our data set in little batches of size 16. If you have a larger GPU, you might be able to do batch size of 34, 64, 128, and so forth. So we're going to select the images of this small batch. We're going to return a tensor. We're going to put it into our CUDA device. Then with torch, no grad, we are going to, the reason why we use no grad is because PyTorch by default computes the gradient of anything that you pass through it. So here we're going to use the model. We're going to unpack the inputs, select the hidden state, take the average of that middle of dimension one, pass it back, put it back into the CPU, and take back a NumPy array to be able to work with this a little bit better. Then we're going to add it to a new column into our dataset called embeddings, and then we're going to return the batch. So here, so that this example takes a little bit less time, what we're going to do is that we're going to shuffle the dataset, and then we're going to take a range of 1,000 images. Right now we have about 9,500. Then we're going to apply the function. We're going to select batch true, and then we're going to put the size at 16. It should take about less than a minute, depending on the kind of GPU that you have available for yourself. As you can see, in mine is going actually quite fast. I don't have the greatest GPU, by the way, but it is decent enough to run examples like this. And then once we do, if we, in particular, if we are going to be computing a large or be doing this exercise or this particular use case with a lot of data, definitely one of the things that we want to do as soon as we finish this is to save the embeddings so that we don't have to use them again. So I'm going to do here vectors, vectors. I'm going to save it with NumPy. And as you can see here, I have a vectors.npy on the left-hand side. Okay, so now the next thing that we want to do when we create a collection, I mentioned that you're going to need a couple of things. You're going to need an ID, and then you're going to need a payload. So for the payload, we're going to select the images that we didn't use to create the vectors. So the image ID, the diagnosis type, the age, the gender, and the localization. Then one of the things that you will notice if you try to use in Qdrant, you don't want to use NAN. You want to use more like more empty friendly data types like none and so forth. But for this particular use case, we're not going to assume any age of a patient. And what we're going to say is we're going to represent the non-available ones. We're going to represent them with a 0. Then, so we are selecting these columns, creating a pandas data frame, filling in the missing values with a 0, and then converting this into a dictionary. That is going to be our payload. As you can see, we have for every image, we're going to have an ID, a vector of 384 dimensions, and we're going to have a payload. The payload is going to contain a JSON object, and that JSON object for each image is going to be a piece of metadata. Okay, so now we're going to create the list of the range of IDs, and we're going to select the number of rows that we have in our dataset. For that, we're going to load the vectors that we created, and we're going to pass them into a list. Now we're ready to upload these vectors into Qdrant. So we're going to select, you can do this in batches if you're doing the entire dataset, or you can do it in one go if you choose to do so. Here, if you are doing the entire dataset, you want to do it in maybe depending on the specs of your computer, you might want to do it in batches of 1,000. I'm going to do here because I have about 1,000 samples. I'm going to do it in batch size of 100. So we're going to upload or upsert all of these points into the collection that we created at the beginning. And then we can count to see how many points do we have in our collection. And as you can see, we have about 1,000. And then we can also scroll through our vectors to make sure that we do have, that our vectors are indeed inside our collection. You can see here, we get back when we use client.scroll, we get back the vectors and the payload, but we don't get back, we don't get the vectors, we get the payload of the vectors. We can change this and say, give me 10, or actually, let's say, give me 2. We can use with vectors. By default, this is set to false. So if you change that to true, you're going to get all of your vectors back, as you can see here. So that's just in case you want to check out your vectors, did they actually come through, and so forth. Okay, so now let's go to semantic search. So semantic search in the context of vector databases and image retrieval refers to a method for searching for information or images based on their meaning or content rather than just using keywords. So we are assuming that that model has created a good representation of the images, and it's much easier to look at a vector at 384 numbers for the computer than it is to look at an image which behind the scenes is three matrices, red, green, of pixels, red, green, and blue. And so it might be much easier for it to allow us to search and compare one vector, one image to another via this 384 dimensional sequence of numbers than by three matrices of many, many numbers. Okay, so let's use the that search method to search through our collection. As you can see here, I'm passing the name of my collection and I'm selecting that embedding from the very beginning of this tutorial where we had the melanoma use case. If you recall, it was at index 8,500. So here we're saying, give me the mean or the average of the first dimension. Give me the first element, because remember it's batch size dimensions. So we just want the whole vector in a get-go. And then we want to limit the results to 10. You can see here, we get a couple of things from Qdrant. So we get a score. So this score says how similar is this image. Then we get the payload. So this is a person. The person that we had was also 55 and had a melanoma. So this one is a benign keratosis-like lesion. But then here we also have melanoma, melanoma, melanoma. So most of them are similar skin diseases. But we do have quite a few melanomas. So a couple of the things that you want to make sure you pay attention to is the score. And then what am I getting here in your payload, depending on the information that you added to it. And then as you can see here, we're getting mixed genders, and then the vector doesn't come back. So, but what if the doctors are evaluating the skin condition of a particular person? Say this person was a female older than 55 years old. So one of the things that you can do with Qdrant is that you can filter your search via different conditions or different criteria, like this ones that we have here. And you can say, well, my search results must have the keyword gender equal to female or sex. And then it should also have the age in a range between greater than or equal to 55. So we want to get a female. So it must is a hardcore rule, and then it should says like, okay, if you see anything greater than or equal to 55, give us back those results. And then the way in which you pass this is you use your client.search again. Here we are assigning this to a variable. We are assigning this search result the variable results. So then we're using the collection, one embedding again, and then now we pass a query filter and we get back 10 results. So you can see here, every single person that we got back is older than 55, 70, 55, 80, and so forth. And then all of the scores that we got are actually quite good. But the lesions seem to be not exactly melanoma. Now, I'm not a skin condition expert, so it could be that these ones are very, very similar. So one of the things that you can do, aside from evaluating the score and evaluating the information inside the payload, is that you can evaluate the images yourself and see whether this makes sense. And one of the ways in which we can do this, so we're going to create a little function that is called see images. And we are going through a range of images, so top K, and then we are selecting from the payload that we got from our results. We're selecting the image ID, the score, the diagnosis, the gender, the age. We are filtering the dataset for the exact same image ID in our results, and then we are getting the image back. So now we're gonna say results at index I plus one, gender, age was diagnosed with a particular disease. And then the score was so forth. And then we display the image. So let's see what we get here. So the result for image number one was female age 70 was diagnosed with actinic keratosis. This image was the score was 0.8765 or 87.65%. As you can see, this seems quite similar or a little bit similar to the melanoma that we evaluated earlier. So this one as well, this one is melanocytic nevi, and the score was 87, and it also seems quite similar to the melanoma that we got earlier. So the representations are working fine. Whatever is in the image is being used to get the most similar ones, or in our image query, whatever is in the image query that we're using. So let's actually evaluate another image. We're gonna select, if you get to this point, you might not be able to select the 7,777 because we selected a shuffle. We shuffled the data set and selected a range, but let's see if it works. I doubt it was going to. So let's see. Because I selected a smaller subsample. So I'm going to say we have about 1,000 rows. So let's see if we can get another one here. Okay, so 777 is available because we have about 1,000 rows. So here we have a case of melanocytic nevi, and then we're going to use that other image to search in the collection. But now we're going to pass into Qdrant the parameter threshold. It's going to be set to 0.92. We only want images that are very, very similar to the use case that we have at hand. So notice what we got. In the very first one, of course, we're going to get the image that we have inside our data set. That's definitely going to be a one-to-one match. But then we're going to get different ones that are above the threshold that we specified. Because why are we doing this? Sometimes doctors have very, very risky situations, and it might be easy to spot a really bad condition, but it might not be as easy to spot a very bad one. A one that could be very bad, but not easily noticeable. And what we can do is give the doctors the opportunity or the ability to assign, I want to be this confident that my image is that the images that I'm going to use to evaluate the one that I have are going to be super similar to mine. And that's why we set up the threshold of 0.92. Then here we have a random range. And then for this random range, so what we will want to do is, so say for example, we wanted to select images from a particular subset of images. Say we have the IDs of images that we know for a fact we evaluated in the past and have a particular skin condition. So one of the things that we can do is select them verbatim. And so just to give you an example here, I'm going to move the 600, the 5,000 to 500 and 6,000 to 600. And we're going to select a range of, instead of 20, I'm actually going to say 10. And then what we're going to do, we're going to act as if this random range was actually containing the images previously selected by a doctor and that they wanted to use for the evaluation. So what we're saying is, so as you can see here, we have ID 510, 540, 550, and so forth. But not all of these ones have the exact same level of similarity to the image that we're looking for. So how did we do this? Well, we use a filter and we pass a must, and we said has ID condition of this random set. So ideally, the doctor will be able to pinpoint, okay, this image, this image, this image. I want to search the most similar ones based on this criteria. And then in this next example, What I want to show you is like, what if dermatologists wanted to exclude specific samples that may have been included twice by accident or as a product of synthetic data, of a synthetic data algorithm? So we can follow the same process as the above and then use the must parameter and the must not. And you'll notice how our search results now don't include IDs in the range we provided anymore. So what we're saying is the reverse. Imagine that the random range that we selected earlier was the range of ID, or the images, the IDs of images that we don't want to include, because we know there's a particular condition that is only unique to that patient. So we can say must not as opposed to must in the previous one. And now, as you can see, we get anything but the IDs inside the range 500 to 600 in intervals of 10. So if the reason doctors are searching for images in a vector database is because they need help to make a decision, then they will most likely want to evaluate images with or without the disease. So let's select another example of melanoma and compare it to images similar to it without cancer and not located in the face or the neck. So here we have a case of an instance of melanoma. And then here we are saying in our filter, we're saying must. The diagnosis must match melanoma, or must not match. So again, we are comparing it to similar images without cancer. So we're saying it must not contain, it must have anything except melanoma and actinic keratosis. And then it must not be located on the face or on the neck. And the cool thing about this particular use cases is that because Qdrant is sitting in the background, the front end developers can be as free as they want, or they have a free range of options to create the user experience or the user interface for the doctors however they want, while Qdrant just gives them the right tools and the recipe to be able to query the images that they're interested in. So here we have the third results. So we're saying my collection, the melanoma, sample 2, and then not cancer, not face or neck. And as you can see here, we did not get exactly melanoma back. We end, if you look at the localization, lower extremity, upper extremity, lower abdomen, back, lower extremity, and so forth. So we were able to use the payload to specify what kind of images from which kinds of patients I want to get images from. And this is particularly really useful if the doctors are looking for specific things, or they want to exclude. They might not know what they want in particular, but they know what they don't want. And here you can see the score that we have quite high scores for these images, even though they don't have the exact melanoma per se diagnosis. We can see the result of 3 images from this sample with the function that we created earlier. And as you can see, this one is melanocytic nevi. And yeah, of course, it's not very great to look at all these images of cancer, but we're doing this for, as it is a very interesting use case and very useful to help people with. So judging by the images above, doctors can have a pretty tough time when it comes to diagnosing people. So some benign diseases like the ones above can often look like cancerous spots, while in reality the patient might not be at risk, and you could avoid having to chop a piece of the skin of a patient or something, or cut it off. So lastly, the last thing that we want to check out is what if the team of doctors working evaluating different samples of skin cancer, each could have its own version of the tool, or we could batch those queries and leave the logic on how to serve the results to the developers at the hospital. So one of the things that we can do with Qdrant is that we can use batch search. So what we're going to do here, we're going to create a couple of filters. The first one is going to be, I want the values in my images, the images that come back, I want them to be in the chest. And then in the next one, but I also don't want any diagnosis that is for benign keratosis like lesions. And then if we evaluate an example, here we have a melanocytic nevus. So we don't have the one that we selected. So we said it must not contain this particular diagnosis. Okay, so then we're going to create one query. And notice here that we're now using the method called search requests. And then what we're saying is, so here is my vector at index 700. And then we have our first filter. So, and then we have the payload selector to exclude image ID and DX type. So what we're saying is we have one doctor. This doctor is evaluating this particular vector right now at index 700. They don't want to any matches back that are contained in the chest. And also they don't need to see the image ID and they don't need to see what was the type of diagnosis. Limit this query to 4. Then in the second one, we're saying this other doctor is evaluating image 770 and does not want any value or any diagnosis of this kind and wants to exclude the image ID, the type of diagnosis, and the localization of the results back. So now we have two search requests that we haven't sent to Qdrant yet, that we just have established. And what we can do is we can batch them together and say search batch, use our collection, and pass in a list with both of the queries. Now, if you notice, we get two lists back. We get, in the first one, we try to exclude the chest, or sorry, we try to only get the localization of matches in the chest. So if you can see, as you can see here, in the first 4, all 4 are chest images of skin lesions. And then in the last 7, for the second query, for the second doctor, we excluded the image ID, the diagnosis type, and the localization. As you can see, we only have the age, the diagnosis, and the gender. And then the other thing that we said for that filter is we don't want this kind of diagnosis. And as you can see, we have melanoma, melanocytic nevi, basal cell carcinoma, and so forth. But we did not get that particular one that we started with. And that's a wrap for today. We're going to finish up so on the semantic search side of things. Now, if you really want to take this to the next level, one of the things that you can do is create a little app to demonstrate what exactly you are doing. And we can do that right now. So we are going to be putting the exact same things that we have been using throughout this tutorial. We're going to be putting it into a script to run with Streamlit. And then we're going to be adding a button to upload an image with any kind of skin condition. We're going to showcase the image. Then we're going to read it, pass it in through a processor, use the same functionality to get the embedding layer that we used earlier, use that vector to search with Qdrant, and then return as many search results as we ask it Qdrant to give us back. Here are the things that we're going to do. For every search in the top K, we're going to showcase the diagnosis, the image ID, the localization, the gender, and the age. The reason we're not showing the image is because we will have to add something like a URL to be able to go and read that image if this was actually hosted somewhere in the cloud. So with that, let's actually write this down, and then we're going to have a file in our same directory called image search app.py, and then we're going to run streamlit run image search.py. We have an image here that contains melanoma. I have already downloaded it to my computer. You can also do the same by going to Google and then put melanoma or any kind of skin condition. Then your app should be coming up. You're going to go drag and drop the file, select your image that you just downloaded, and then Qdrant is going to do the rest for you. So this is the same image as you saw before. Here's the image and much larger. And then here we have another one of melanocytic nevi in the upper extremity, gender male, age 35. So we have all of them, all of our results are the same. And you can play around with this and you can change how many search results you want to retrieve and so forth. And then not only can you use one image, but you can use multiple images at the same time. So I encourage you to continue playing with this and also check out the last few, the section called Final Thoughts, which has a few links to tutorials that will be very helpful for you to um, learn more about these technologies. Qdrant for semantic search, how to do semantic search with image data. And yep, I hope you find this useful and these resources useful as I did. And see you on the next tutorial.